Okay. Can you guys hear me?
Yes.
We're still missing a few people. My internet has been pretty hit and miss this morning, so hopefully I won't cut out. But if I do, don't worry about it. We'll just pick up things on Friday. So I have paper down here because I'm gonna write some things that are in the notes, but if I write them, then I can talk over my writing so that you understand it a little bit better. I think I posted homework 5 because my internet was so bad. It was hard for me to go back and check what the bright space to make sure everything was there. But I don't know if anybody check bright space to check. It's right. The homework 5 is right after homework 4, right above notes 12. So if somebody wants to get into bright space and let me know it's there, go ahead and do that. Just interrupt me and let me know it's there. The other thing is if I get through today, on Friday, one of your 3 homework problems is writing a Visual Basic program in Excel as a macro. And so we talked about that earlier on. And I can't remember. I don't think I gave you a problem with that yet. You guys have not done a homework problem where you've had to write a macro, correct?
Dr. Jeffrey, it's posted.
Oh, okay. Yeah, I see that in the chat. Somebody said it was posted too. Thanks. I think PAL is down because it's not working for me, so I'm on my phone. Yeah, I think that's the problem is there's some computer glitch at the university because I was having problems. One of the things I always hook up to, and you guys should do this too, I have this Cisco AnyConnect right here on my screen. Oh, you guys can't see it, but it's a virtual, what is it? Virtual network, VPN, um, virtual personal or private network. So Purdue, you can set them up through Purdue so that when you log in, it goes through some security things so that it's just safer than, just getting on the internet wherever you are. Set up a VPN system and it works. And I couldn't get on that this morning through Purdue, so something was wrong. I think they have been having some problems because they were having some problems with one of their softwares, and I can't remember what it was. It may have even been WebEx. So the homework is there. So, and my thing just undid it again, even though I didn't do anything. The one problem is a macro, and you guys have not written macros yet for your homework. Is that correct? You would remember it if you had.
Dr. Jeffers, didn't we do it for Euler's method?
You did it for an Euler's method, and so you guys have done it. Okay. I can't remember what problem somebody said no. You've never written one from scratch. That's true because all you have to do is modify the program I've given you. So that's what I want you to do on the homework too, is take the program that I've uploaded, the Visual Basic Complete program, and you can modify it the same way that you modified it last time. Okay? So we'll talk about that on Friday. I may even sit down and go through it and modify it because there's so many people in this class. Some of you may be having problems with that, but I'll go through it. And I think I remember I did go through it almost verbatim to do your last homework. So I'll do that again because it is new and some of you do not like programming at all. But programming is logic, and you have to just read each line of code and make sure it's doing what you think it's doing. So, okay. So last time, I'm going to put these up here, and hopefully it'll focus on that. Last time we talked about BOD, L, breaking down and causing a deficit, D. Okay? Now, you guys can see this, right? The rate constant here is KD because that's the in-stream rate constant. D, though, reaerates and goes away by a reaeration rate constant, A. And interesting, sort of an aside here, if we do Ka times D as our term, that's like the same thing as writing Ka times the oxygen concentration that is saturated minus the oxygen concentration that is actually in the stream. So this is our actual oxygen concentration. This is the saturated value. So if you have an oxygen deficit, if this is the saturation value, O2 sat here, eventually even if this is just a tank of water and you sparge it, you're going, if you start off with 0 oxygen in the system, this is time, obviously, on this axis. If we take a bucket, put water in it, but deoxygenate the system so there's no oxygen in it, we can do that by aerating with nitrogen. We can do it by adding a chemical that reacts with the oxygen. But then if we start aerating it or sparging it, the oxygen concentration will come up. And the rate of increase is a function of the deficit. So it is directly a function of this deficit, the difference between this. So when our oxygen concentration approaches our saturation value, our slope is really, really low. So we have a curve that looks like this because at the maximum deficit, where the deficit is the highest, remember, this is a rate. It's a change in concentration over change in time. So we have a rate of reoxygenation when our deficit is the greatest. Okay, so it is just Ka times deficit. For every organic molecule that breaks down and utilizes oxygen to do that, because the bacteria are doing this. So over this Kd, I could put bacteria because and other protozoal microorganisms, because L goes to deficit. L again is BOD, but it's BOD that consumes oxygen. It consumes oxygen, creates this deficit. Okay. L also within the stream can sediment out. Okay, and form deposits of sediment within the stream. So we have 1, 2, 3 reactions. We have two things that we're going to model in this system, and we're going to put this in our stream reach. So we're going to put basically an initial value of L, an initial value of D here, and over here we're going to put L plus some change in L, and we're going to put our deficit plus some change in deficit over here. We've got water flowing in upstream. This is our stream reach. Our stream reach, we're doing calculus on this, so this is basically infinitesimal small, right? Delta X here. But that gives us a volume here. And we also have reactions occurring in here, and these are the reactions that are occurring in here. So if these reactions occurring within this control volume, we have 2 substances, L and D. D, you don't think of as a real substance, but it's a difference between a constant value, the saturated oxygen concentration in the system, and the actual concentration of something. So D is a substance in a way, it's oxygen, but it's a funny way of monitoring oxygen. So this is our stream reach. Remember our basic environmental equation is a mass balance. Accumulation equals inputs minus outputs plus or minus reactions. And we put plus or minus because it could be decay, it could be growth of a substance. In fact, this process is growth of deficit, and then we've got decay of deficit. Okay? L is breaking down by 2 substances, but we can add those together and get a KR. KR is the sum of KD plus KS, because these are both pseudo first order processes. So we can add up the pseudo first order rate constants because these are both per time. 1 over days are the units on these rate constants, on all of these rate constants. In fact, this Ka is per time because this has units of concentration. If we write over here D deficit, D time, then this is per time. That means the Ka is per time. So even our reaeration rate constant is per time. Okay? What did I say last time? Doodle a lot. Because if you doodle a lot, you understand it. You have to draw to conceptually understand what is going on with these problems. Accumulation equals inputs. So we have to do this accumulation on both L and D. That's two separate equations. The first one is pretty easy. And again, we're doing this in our control volume as a function of time. But immediately we're saying we're going to apply steady state to this because at this point we have a constant value. L naught, because we have a pipe or something that's going in here, maintaining a constant value at some point along the stream, downstream. So our accumulation is 0 because we're going to solve for the steady state case. And remember, steady state, I can spell, steady state is whenever you have inputs and outputs. Equilibrium is when you have no inputs or outputs. So our inputs are then Q times L minus Q times L plus some change in L. And then reactions. We have two reactions, but I can sum up these two reactions because it's KD times L, KS times L, so I can factor out the L, and I get the sum of the two rate constants. So for L, we get minus KR, because that's the sum of the two rate constants, times L times our volume. Because we multiplied this side by volume, we have to multiply this term by volume, because normally it would be just dL dt equals minus KR times V for the reactions that are occurring within here. But we're going to multiply both sides by volume. That means that this is milligrams per liter times liters, which is milligrams per day. So this is basically milligrams per day for our mass balance. This is milligrams per day, this term is milligrams per day, and this term is also milligrams per day. So we have all of the same units here. This term cancels with this first term here, and we can divide by V, and we get 0 is equal to, but we're going to divide by V in both cases. Okay, on this side and this side, because we know that Q and V is equal to the area times delta X, and Q is equal to the average velocity times the cross-sectional area. So if we substitute this up here, we get average velocity times cross-sectional area, right? Divided by V, which is cross-sectional area. We have a delta L here, over here. We've got these two terms except for our delta X. And we're going to write our delta X right under our delta L because they kind of go together, right? Minus KR times L. We can rearrange this, and now we get our ordinary differential equation, dl dx, and A cancel, and that's equal to minus KR over mu times L. Okay, and this is first order. This whole term here, KR over mu, is a first order rate constant, so we could well, I'll just do it. This over L, integrate, and then we're going to do minus KR over mu, and we're going to bring over the dx on this side. We're going to integrate from x equals 0 up to some value of x. We're going to integrate from L at x equals 0 up to some value of L at x. right? And when we're all done with this, because the integral of dx over x is log of x, we get L is equal to L naught e to the minus kr over mu times x. And remember, we said x over mu is kilometers over kilometers per day, which is time. So we could substitute in here time, travel time in our stream if we wanted to, but we can leave it in as distance. So this is the answer to our first problem, to our L going into our stream. Okay, let's solve for the second part now. The second part is trickier. This is a good test question, but since we don't have tests, you don't have to worry about it. We're going to do the same thing. d over dx times the volume. This is our accumulation term. Hold on, I need some coffee. Okay. This is our accumulation term. Our input term, same thing. Q times D. Our output term, minus Q times D plus some change in D. Now, what do we do with the reactions? We have two reactions on this. We have L being broken down to form deficit, milligrams per liter of BOD breaking down to 4 milligrams per liter of oxygen deficit, and then that oxygen deficit gets reiterated away. Milligrams per liter deficit gets reiterated away so that we have oxygen in our system. So we have two reactions. We have two arrows going to or from D, so we have to put both reactions on. The first one is a positive. It's creating deficit. It's KD times L. The second one is taking deficit away. KA times D. And we have to multiply both of these by V. Okay, because we multiplied this side by V. We're going to solve for this at steady state, which means this goes away, which means this first term and this first term, because this is QD minus QD, that goes away. That means we have here, again, the same thing. Our Q is equal to our average velocity times our cross-sectional area. We're dividing by V, which is our A times our change in distance for our small little reach, times D. So we have a delta D here, delta D here. We bring the V over. V is A times delta X. The A cancels with the A. This is a minus sign. And then we have a plus, because we divided by V, we have a KD L minus KAD. We can bring this to this side now, the change in deficit over the change in distance, and we'll leave the mu times this term here, just for the time being. We have this term we can bring, I'm going to bring over. KA times D is equal to KD. L we know. We just solved for L. It's L naught e to the minus KR times X over mu. So we can put that in here. because we know L is a function of time. L is equal to L naught e to the minus kr times x over mu. Okay? What does that look like? You have to unmute and tell me. Looks like the integration formula. dy dt plus p of t, small p of t, times y is equal to q of t. This term actually now is a function of, I've written t over here, this is x, it's, you know, it's our variable here. So this is a function of x, this, you know, or t, whatever. It is, we do have an x in here, so that's right. Here we have a simple value because our y is our d, and so our p of t is just simply ka. And we know that p, capital P of t, is equal to the integral of small p of t dt. And so we can do this integral ka times d, whoops, excuse me, because now I'm working in x's, not t's. Dx, it's equal to ka times x, okay? Because our second term, we're assuming our integral goes from x equals 0. And so our second value is 0 because x is 0 at our initial point where we're going from. So we know capital P of t, and the solution to this, if you remember, is y is equal to y naught e to the minus capital P of t plus e to the minus capital P of t times the integral e to the capital P of t q of t dt. So you don't need to memorize this. You know this from your notes. You can always look it up whenever you need to and solve these kinds of problems. If you now plug everything into here from this, because we know, oh, the other thing we have to do is, in this equation, we don't have the y. So I'm sorry, I blew this. We have to divide by, not the y, I mean the mu. We do have to divide by the mu. So this actually over here, it becomes a mu over here. So I'm just going to rewrite it so it's clear as mud, right? So the capital P of t is now ka times x over mu. Once we get rid of that, we've got ka over mu is now our P of t, and we've got a mu over in this term too. Okay, so that was my mistake. Usually you catch them as you go down because it's like, uh-oh, what do I do with this term? So now we can write our deficit. Deficit equals the initial deficit at x equals 0, e to the minus ka times x over mu plus e to the minus ka x over mu times the integral of e to the minus or plus ka times x over mu, right? Times q of t. Q of t is this whole thing. So we have to put this whole thing into here now. Kd times L naught over mu times e to the minus kr times x divided by mu. And then the last thing we have to do is multiply by dx. And we're evaluating this from x equals 0 up to some value of x. we're close because now all we have to do is do once integration. And this looks like a nasty integration, but it's really not that bad. We're going to combine terms. So I'm going to just work on the integral right here, right now. These values right here are constants, so I can bring them out. This value is to the a to the x, b to the x. I can combine these two terms if I want to. Okay, so I'm going to bring out the kd times L naught over mu and of my integral, and then I'm going to combine these two terms. It's e to the ka over mu minus kr over mu times x. This is positive, this is negative, and that's all d of x. So all of this is constant because we're working at steady state. So that means our flow is constant. We're assuming constant coefficients, constant Ka, constant Kr. So this is E. This looks really, really complicated, but it's basically e to the ax dx. And you know how to integrate e to the ax dx, right? So this bringing it down again, kd times L naught divided by mu. We have to evaluate it at the limits from x equals 0 up to some value of x. This thing is itself because it's e to the ax. Chain rule of calculus. That's all I'm using here is the chain rule of calculus. So if you forgot your calculus, go look up chain rule. Divided by the a term. And now I'm going to just I'm going to be simple and do that. Okay? And when I expand this out, almost all of the times when we do expansions, the second term drops out. But in this case, it doesn't because this is e to the x. E to the 0 is, somebody tell me?
1.
E to the 0 is 1. So I have to account for the second value. And so these first two terms, and you never thought you'd see calculus again, right? This I can bring out Ka minus Kr. I can put the mu on the top because it's in the denominator of the denominator, which means that I can move it to the numerator. It cancels with this term, right? If I move it up to the numerator from the denominator of the denominator. And so I brought this term out because it's multiplied by both of the terms. And then I end up with e to the Ka over mu minus Kr over mu times x minus e to the 0, which is 1. We're almost there. Now I can put this whole thing back into this expression. Whoops. I can put this thing back into this expression right here. So I'm going to rewrite this expression. D is equal to d naught e to the minus Ka times x over mu plus e to the minus Ka times x over mu. And now I've got everything that is my integral. And so now I can take my integral term and multiply it. I have here, I'm going to bring this term first. E to the Ka mu and I'm going to bring in the X there. And I'm going to expand these because this is minus, so I can multiply them. E to the minus KR times mu to the X minus 1. Those are multiplied together. And then I have KD L naught over KA minus KR. This term multiplied by this term, this is a minus Ka, this is a plus Ka. E to the plus 1 times e to the minus 1 is e to the 0. E to the 0 is 1. So this times this basically is 1, and I'm left with this term. This term times this term is this term. So when I'm all done, D is equal to the initial value minus Ka times X over mu. When I rearrange, I'm going to bring this over because these are all my constants. KD times L naught over Ka minus Kr. And then this times this is 1, so I'm left with this term. E to the minus Kr times X over mu minus this term times 1 is e to the minus Ka times X over mu. Okay, and we have our answer. So this is the Streeter-Phelps equation. It says the deficit is a function of Ka. It's a function of the stream velocity. It's a function of Kd. It's a function of Kr, which is the sum of Kd and Ks if we have sedimentation occurring. It's a function of distance downstream. What else is it a function of? And this is assuming we have constant cross-sectional area, constant flow rate, and other constant coefficients. So you wonder, how practical is this model? It's extremely practical if you know general size of the stream, and if you want to calculate what the effect of waste getting into the stream would be, if you have an idea of what these rate constants are for BOD utilization within the stream. The take-home message of this is that as the stream, with the stream distance, BOD looks like this. L looks like that. But deficit, I could have, or let's do this as oxygen. Oxygen looks like this. Because maybe this distance right here is my deficit. So if I wanted to plot my deficit, I start with an initial deficit here, and it would go up, and then it would come back down and look like this. Once I've utilized most of my L, my deficit curve starts coming back down. Okay, so this is deficit. So we have L going away by a first, and this is distance downstream, but it's also time. So as my BOD goes away in my stream, as my organic material that is causing a deficit goes away in my stream, well, as it's being utilized, it's sucking up oxygen because, hey, it's respiration, right? And as the respiration is occurring, my oxygen concentration goes down. The oxygen is always being reaerated. Oxygen is always coming in from the atmosphere. But remember, at this point, oxygen is coming in very slowly because my initial deficit from saturated, if this is my saturated value right there, and it's eventually going up to that saturation value, right? So I have a little bit of initial deficit here. This value down here is also D naught from there to there. So I have some initial deficit. I've just made up I have some initial deficit. I don't have to, but I have some initial deficit. So eventually when my stream recovers, the oxygen should go up to its saturation value. Once I've metabolized all the organics in the water that are being sucked up by bacteria, creating oxygen demand. Obviously, when you have bacteria in a stream, you always have a little bit of background deficit because even the bacteria undergo endogenous respiration and things like that. So there's usually, especially in the summer, diurnal oxygen swings because a little bit of algae in the water, you have oxygen production during the day, you have more oxygen consumption during the nighttime. So you have lots of things that affect this curve over time. But this is a snapshot in time of what a deficit curve looks like. If you are, again, at this point, this is an important point, is in our stream here, this is distance, and at this point, we're pumping waste into our stream that is then going down. So we have a flow in our stream here, but we're constantly putting in waste here. So our L is coming in from our industry or our wastewater treatment plant. And in this case, our deficit curve looks like this. Really, if we're just piping contaminated water into our stream. And so if you don't have a wastewater treatment plant, you get this curve. If you do have a wastewater treatment plant, you get a curve that looks like this. Because now you're not putting enough, the amount of L naught that you're putting in is so low, you don't build up a deficit in the stream. Okay, so a key parameter here is how big is the L naught. If L naught is very, very high, you end up having an oxygen sag curve. And they call these a sag curve because it sags down here. So this is an oxygen sag curve. It happens when you throw in, 300 milligrams per liter of oxygen into the water, and all of that oxygen, all of that organic has to be consumed by bacteria, and it drives the oxygen concentration low. It could actually drive the oxygen concentration to 0. And then in that case, hey, all the fish die. So if you get a wastewater treatment plant that all of a sudden has some upset and it's not working properly, power goes out and it doesn't have backup power, and all of the waste goes directly to the stream. Hey, all of the fish in the stream die, and then you got a stinky stream, and it takes a while for that stream to recover. Okay, so you have problems with streams if you don't have adequate wastewater treatment, but you can also have it occasionally if you have upsets to the treatment plant where the treatment plant fails outright for some reason. And that often happens during like storm events and things like that, where the electricity goes out, backup power is not working, the water coming in is just too much, and it doesn't work. Okay. So how's that? Now you know your math, and hopefully you were able to follow me through each of these steps. And all of these steps are outlined in the notes. So it's 12 after right now. Let me go back to the notes and I'll show you them. Okay. So we talked about this as being our little schematic. BOD, which I've used as being L, goes to deficit, gets reaerated back. And again, on our oxygen curve, someplace there, this is DO, or dissolved oxygen. I should put this as O2. It's because it's molecular oxygen. It's a sag curve and then it recovers. If you plot the deficit, then it goes up and then back down. This, again, like I said, does not happen if your wastewater treatment plant is working right. But if you have a pipe discharge, and this happens in developing countries where the water is not treated, the city's discharging raw sewage to the water, and so you downstream, you have no oxygen in the river, you have no fish in the river because the stream is highly polluted. In those cases, the biggest problem is not the oxygen deficit in the water, it's all of the other things. Because if you've got 1 million people in the city, they have every disease. And then that means that the viruses, the bacteria that are in the feces that are flushed down the toilet all get to the stream, and you don't want to come in contact with that stream because of the diseases that you can potentially get. So oxygen deficit is one thing, but just even being in contact with water that has human feces in is another thing. So in a lot of areas in the world where the sewage is not treated and people know it's in their stream, they don't go in the stream. They don't touch that water because they know it's contaminated. Okay, and it's just been recently, like in Medellin, Colombia. It's been within the last 10 years that they put in a wastewater treatment plant. So, and that wastewater treatment plant probably captures about 80% of the waste from the city, which means 20% is still piped in directly into the Medellin River, and still creates some problems in the river, and enough problems that I wouldn't swim in that river. Okay. Here we did our deficit. Remember, we had our two reactions. We rearranged it. We got it to this form, and we substituted our value for L in here. And then we solved it using our integration formula to get this, which is the Streeter-Phelps equation. If you notice, it has 3 parts. It's got 3 additional terms. This is the initial deficit. So this is decay of initial deficit by reaeration. These terms go together. If I've got some deficit, that deficit is going away because of Ka, because of the reaeration rate constant. And this is a decay. It's a decay in deficit, which means I'm reaerating the water. This term then is a reaeration term, and this term is BOD utilization. And at some point, this term is equal to this term. But this is production of deficit through BOD consumption. This is decay of deficit caused by reaeration. This is the decay of deficit that is caused by the BOD that is being put in at that point discharge. Okay, whereas this is background deficit because it's D not. It's a deficit that's coming in the stream itself from upstream. The initial deficit that at point X equals 0. Okay, so for example, up here, I don't know if I have it. I have an initial deficit here. So the distance between the saturated value and where this is some initial deficit that is coming in to this reach from upstream. That's what this first term is. If you have no initial deficit in the stream, Streeter-Phelps simplifies to this equation. Evaluating it, you can evaluate it different ways. Field sampling, you can measure the bottle KD value. There are lots of literature values for Ka estimates because the reaeration rate constant is largely based upon the stream geometry. The deeper the stream, the lower the Ka. The faster the water is moving, the higher the Ka, because there's more turnover, more turbulence, and so you have larger reaeration. So if you're in a mountain stream where the water is bubbling over rocks and things like that being mixed, the reaeration rate constant is really, really, really large. If it's a Wabash River and it's meandering slowly, the Ka may not be that large. So Ka depends upon mixing due to velocity gradients, temperature, wind. So on the Wabash, on a windy day, you have a lot more oxygen transfer into the water because you have mixing at that surface layer. Okay, ice cover. If you have ice cover, you have no oxygen transfer. But if you have ice cover, that means that before the ice formed, the water was probably had lots of oxygen in it because as you go down in temperature, you go up in the solubility of oxygen. Surface films, morphology, like dams, which if you're designing a dam, this is an interesting thing because where do you take the water from to put downstream? If you're designing a large dam, do you want to pull the water from the top or do you want to pull the water from the bottom? The water from the bottom is cold. It may be low oxygen. The water from the top could be warm. It could be even higher oxygen because it's closer to the surface where reaeration is occurring. So how you design your dams and what water you want to put downstream actually makes a difference from an ecological standpoint. There are formulas for calculating Ka, Churchill formula and other things, and it's about time to go. So I'll end there. We'll go over some of these later concepts there on Friday or Monday. I'll try and help you with the homework on Friday. Okay? Everybody's going off.
Thanks, Dr. Jeffrey.
We'll see you on Friday.
See ya.
I'll have homework before then, and then I'll try and help you on Friday with the homework.
Oh, for sure.